Let's try to understand the law of large numbers by looking at a simple example of tossing a coin. So when we toss a coin, the probability of getting heads is equal to half, and the probability of getting tails is equal to half. Now, if we toss a coin, let's say 4 times, so the question is, can we expect exactly 2 heads and exactly 2 tails? Now, if you toss the coin 4 times, this probably will not happen. It's possible you get maybe 1 head, 3 tails, or maybe 0 tails and 4 heads. Anything could happen when it's a small number of trials. So then the question is, why is it 50-50 then? If you toss a coin 3 or 4 times, or maybe 6 times, you may or may not get 50-50, like exactly the same number of heads as tails. But if you increase the number of trials, let's say you toss the coin 4,000 times, then it is possible that the number of heads is pretty close to number of tails. It could be equal or very, very close. So that is exactly what the law of large numbers says. If a certain process is repeated over many, many trials, then the proportion of trials in which event A occurs will be pretty close to the probability of A, the theoretical probability of A. So as we keep increasing the number of trials, uh, the probability of occurrence of some event in many, many trials will be close to the probability that we calculate for that particular event. Now, if we look at the first example, a die is rolled 1,555 times. How many times would you expect to get a 6? So if a die is rolled, theoretically, the probability of getting a 6 is exactly 1 out of 6. Now, if you're going to roll it 1,555 times, that is a large number of trials. So you can expect 1/6, about 1/6 of the total number of trials to be 6. That is the expected number of 6s that you're going to see in 1,555 rolls. So when we do the calculations, that is 1/6 of, so times 1,555 is about 259, approximately 259. And that is the number of 6s that you're likely to see when you roll a die that many times. Let's look at the second question. Suppose a person who has a habit of driving fast has never had a traffic citation. What does it mean to say that the law of averages or the law of large numbers will catch up with him? Is that true? Now, the law of large numbers says that if we are repeating a certain trial many, many times, and we are looking for a certain occurrence of a certain event, A, then if the number of trials is large enough, then the proportion of times that a certain event A occurs in those large number of trials is equal to the probability of A. Now here, what are we doing exactly? This person drives fast. There's a certain probability that is out there of getting caught when you drive fast. So if you drive once and you're driving fast, the chances are you're not going to get caught. But if you're on the road many, many, many times, and each time you're speeding, then what happens here is the number of trials, and in this case, the trials is driving on the road. So the number of trials has become large. So the proportion of the times you get caught will roughly equal the probability of getting caught while speeding. So at some point, a person who's speeding constantly every time he or she's on the road is going to get caught, and that is by the law of averages or the law of large numbers. The next one, we consider a game. It's a two-player game. A die is rolled, and you get $3 if an even number is rolled, and you give your opponent $2 if an odd number is rolled. 100 games are played. The expected payoff for an even number. So if 100 games are played, the probability of getting an even number is half. The probability of an odd number is half. So half of the games, so 50 of the games, you're going to get an even number for which you're going to get $3. So 50 times 3 is positive 150, and that is the amount of money you can expect in 100 games. What is the expected payoff for an odd number? So out of the 100 trials, we can expect 50 to be even and 50 to be odd. But if we get an odd number, we're going to lose $2 to the opponent. So that what the amount of money we lose would be the negative 50 times 2, which is equal to $100. Now, what is the net profit if you're playing 100 games? You're going to win some, lose some, but let's figure out what your net profit is. Your winnings are 3 times 50, which is 150. Your losses are 2 times 50, which is 100, but you come out in the positive. That is a net gain of $50. And this is for 100 games. But if you want to find the average profit per game, because here the total amount of money you're going to make in 100 games is $50. But what's the average amount of money that we'll make per game? So that would be the total profit, which is 50, divided by 100, which is the number of games. So that is 50 over 100, that is 50 cents. Now here we're going to do a few problems where we're going to figure out the expected value of certain games, and expected values are applied in real life. You're going to see some of those examples pretty quickly. Let's look at the first example on this page. A game is being played between two people. They decide to play the game. A single die is rolled. If it shows a non-prime, Tom receives points equal to twice the number of dots showing. So there's for rolling a non-prime, you get twice the number of dots showing. If it is a prime, Tom loses 3 times the number of dots showing. What is the expected value of the game? So in this case, first, in order to find the expected value of the game, we need to set up some information, and it is a good idea to set it up in the tabular form so that way you're not confused. So make sure your table has at least 3 columns. Payoff, that's your first column, probability of the payoff, and payoff times the probability of the payoff. So basically multiplying these two numbers gives you this. So what are the things that can happen when you roll a die? You could get a 1, a 2, 3, 4, 5, or 6. So these are the only possibilities. We know that for each possibility, there's a probability associated with it. So for rolling each number, the probability, if it's a fair die, is equal to 1/6. We make sure that all the 1/6 add up to 1, so we know our probabilities are correct. Now, what do we mean by payoff? Payoff could be money in the form of money or points in a game. So if we roll a 1, 1 is not a prime. So if it's not a prime, then we receive, which means we get positive twice the number on the die. So that would be 2 times 1, which is equal to 2. The next one is rolling a 2. 2 is a prime. So what happens when we roll a prime? When we roll a prime, Tom loses points equal to 3 times the number of dots. What's 3 times the number of dots? 3 times 2 is 6, but he loses those points, and that's why we have the negative. 3 is again a prime. We lose 3 times the number of dots, which is equal to negative 9. 4 is not a prime, so we win twice the number of points, which is 2 times 4, that is equal to 8. 5 is a prime. We lose, so it's negative, 3 times the points that are seen, so that would be negative 15. And when we roll a 6, we roll 2 times the number of dots on the cube that we see, so that would be 12. So sometimes we win points, sometimes we lose points, depending on whether we roll a prime or a non-prime. So what's the next step? We've written down the probabilities of those payoffs. Now, the third column is basically multiplying the corresponding numbers in column 1 and column 2. Now, adding up all the numbers in the last column, we get negative 1.33. So that is the expected value of the game for Tom. So what does that number really mean? It means that if Tom plays this game over and over and over again, many times, then he can expect to be or to lose about 1 point in every game. So basically, the long run average of number of points that Tom makes per game is about negative 1.33. In the second game in example 3, we're rolling a biased coin. So it's not a 50-50 chance of getting heads or tails. So let's see what's given. The odds against getting a tail is 1 to 2. Just remember the definition of odds against an event. Odds against a tail is probability of the opposite event, which is probability of getting heads over probability of getting tails. So that is 1 to 2. So what that means is probability of getting heads is 1 over 3, and probability of getting tails is 2 over 3. That's how you can get 1 to 2, and that is the probability. So probability of tails is equal to 2/3. Probability of heads equals 1/3. Now, when 2 coins are tossed, these are the total possibilities: heads, 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 tails, tails, heads, and heads, tails. So the probability of each event can be calculated using the probability of tails and heads. So what is the probability of matching heads? That is heads and heads. Multiply the two probabilities because of the word and. The first is heads and the second is heads. So that's 1/3 times 1/3 is 1/9. Probability of matching tails is probability of tails first and tails again. So 2/3 times 2/3 equals 4/9. Probability of heads first and then tails, tails first and then heads can be figured out similarly. So it's heads first, so that's 1/3 times 2/3, which is 2/9. 2/3 times 1/3, which is 2/9. So we've got all the probabilities, and if you want to double check, they all add up to 1. So now let's figure out how this game works. We need to find the expected value of this game. So the payoff can be $5 for matching heads. For matching tails, it's $3. If they do not match, then we lose $2. So losing $2 would be negative $2 payoff. So here the payoff is actual money. We win $5 for matching heads, win $3 for matching tails, lose $2 if they do not match in either way, like heads, tails, or tails, heads, they do not match. So we've covered all the events and the probabilities all add up to 1. So the last column is payoff times the probability of payoff. So that would be 5 times 1/9, which is equal to 5 nines, 3 times 4 nines, which is equal to 12 nines. So similarly, we keep multiplying the corresponding numbers in each row. And we figure out these numbers, add them all again, and that gives us a 1. So when we add all the payoffs times the probability of the payoffs, we get a 1. And that is called the expected value of the game. It's the expected value of the winnings per game. So if this game is played many, many times, so that is in the long run, you will make about $1 per game on an average.